Let me see. Whoops. Yes. Okay. That's perfect. I think today's session is actually going to be a little bit shorter than usual, just because there isn't a lot of mathematics involved. But essentially, if you're gonna, for example, work in a research lab or just trying to do a project on your own, this is actually the stuff that you would really be doing, because this is actually what we're trying to do in the fixed process to update the weights of your neural network and actually make your model work. So this is essentially the most important part of I would say this is the most important part of student training. So for like student who trying to train their neural network. So without further ado, we'll just dig in. So as usual, we're gonna do a small recap of last week's gradient descent stuff. So because today we're actually gonna talk a little bit about how weight updates and how we create our training cycles in order to better update our weight. So would also require us to know a little bit of last week's knowledge content. And we'll go through this week's content in a pretty linear fashion. And I also included a lot of other content that was not talked about. Hello, that's okay. No worry. Don't worry. We don't have, I mean, it's midterm week. So thank you for being here. And this week, we're just gonna talk about some of the training stuff, and plus some of the things that was not talked about in the Coursera courses, but I think is essentially pretty standard to know. And I think if you take any courses like APS 360s, you would also go through knowledge content like that. Okay, and we'll go through this week's quizzes, and we'll do a general Q&A session. Essentially, if you have any questions, just ask. If I don't have the answers, essentially we'll try to answer it, and later I'll figure out the answer of the question as in like a message in the Discord channel or such. Anyway, so let's do a recap. Let's do a recap first. There's only pretty much one thing to recap, is what exactly is gradient descent, right? So essentially, in short, gradient descent is we're updating the weights according to the gradients of the loss function that we essentially calculated according to our forecast process. We basically compare our predicted outputs through our model to the standard outputs, or sometimes we also call it true labeling. And then we update it by a small step, which is the alpha constant. It's not necessarily a constant, but in this slide, just recognize the alpha symbol as some sort of increment step, right? It's not necessarily constant, as we'll mention later in this sessions. And that's pretty much the recap. So I just want to remind you guys that if we're going to update our weights, we first need to calculate the loss according to a true label for supervised learning, right? And this time I'm actually going to pretty much show you, if we have extra time, I probably will just show you, like what exactly did I do in one of my lab. I created the basic training process. I can show you what exactly is the training code and see what happens when the code expands. So I didn't include a lot of code in it just because this course is mainly based on TensorFlow. But for most of the machine learning course that's in U of T, it's actually in PyTorch, just because it's much more, like sometimes flexible than TensorFlow. And it's a little bit more robust. So for the first thing that we're going to talk about today, training validation testing set. So this is essentially the first step. When you start to training something, for example, like a model, what happened is that usually you would just have a large set of unprocessed data. And after you process data, for example, if you have different sizes of image, if you have like black and white image and some colored image, you might try, first thing you might try to do is like maybe resize them, maybe crop them. And the second step is like, correct the color channels. If it is RGB, you correct it to black and white and things like that, right? And in this case, we're looking at the training validation testing set. This is essentially the first step after you complete processing data. Or sometimes people also take this factor into the pre-processing step. So they kind of do this in the pre-processing. They sometimes when they're like dividing the data into folders, they kind of just divide it into 3 sets, such that they don't have to like do that job when they're loading in the process data. But essentially what it means that if you have a large group of data, we need to decide how many, what's the percentage of data are we going to use to train our model, and how much data we're going to use to validate our model, and how much of these data sets are we going to test the model. And you may be wondering, what does training mean? What does validation mean? What does test means? And if you didn't ask that, that's a really good question, okay? So basically, training sets, as the name suggests, you use it to train your model. So what happened is that we're looking at these set of data. We're actually putting our model through these data. And at the end of each batches, for example, you update your model. So you update your model through the outputs of your model using these type of training set. So this means that your model actually like look at these data, okay? It processes this data, you input it into your model, and you have some sort of outputs at the end. And you use this to train your model, because your model will update its weights according to the output at the end. Is that clear? Okay, perfect. Now we get to the confusing part. So validation sets and test sets. This is the part that I kind of confused when I first get introduced to this, because I was wondering why I have to have a validation set. Turns out, your model, except for the standard weights that we talk about, that we update, using the forward passing and the back propagation process, we still have other hyperparameters. For example, as what we showed before, the step. Sometimes we also call it learning rates. We have to decide, do we need to take a big step because our essentially our training efficiency is too low. So we want to increment more in each step, such that the training progress faster. Or are we actually taking too much of a step that we actually are skipping some sort of global minimum, right? So that's actually one of the very important factor, which we'll talk about later. It's called learning rate. And this step, the validation set is not for the model to look at and kind of update their weight according to it. So usually in the training set and validation set, we don't update weight according to a validation set. It's just something that we compare, that's kind of use like a test set for each batches or small group of the training set to make sure that the training set is not overfitting to these type of data, just because the model is not adjusting themselves according to this type of validation set. So you actually don't look at your model doesn't look at this type of data, and thus it has no idea whether it's producing some sort of output that's really following the true label, or it's just diverging really fast, right? So this is what human look at. And we later, if we see like the training curves, we might see diverges. So that means that our training set's accuracy is at like 88%, but our validation set's accuracy is actually at like 20%. That means something is wrong. So this is for human to look at and to predict if your model is like overdoing it according to the training data or not. So is that kind of clear to you guys? Yes.
Is there anything like that's different in the validation set? Is there like something specifically look for validation set, or you just randomly?
So let me ask you questions. So what's the purpose of validation? Actually, I will ask you that because I think it will be a weird question. So for the validation sets, what is purpose? It's for human to look at and for comparison in terms of for the training set and the validation set. So you're actually comparing your validation set to the training set to see whether it diverges or not. Do you want those to be artificially different? No. You want they essentially from the same group of data. And essentially after you divide it, you want basically, if you're gonna test whether the apple is good or not, if you pick one, do you want to pick an orange? No. So you essentially want to put exactly one of the commonly produced apple and see whether this type of apple follows, the product standard essentially. So in this case, we want the validation set in the exact same format as the training set, such that when later we look at the model training, the validation set essentially, can give us a predicted outputs, or it give you the general train of thought. But sometimes you didn't intentionally do it, but if you didn't split it correctly, for example, if you have a group of data, which is cat and dog, and you want essentially 60% of those data be training set, but you didn't, you forgot to randomize it, for example. Then you have 50, for example, dog pictures and 10 cat pictures. So your input data is imbalanced. But for a validation set, essentially, if you have all cat photos, your model will give you a diverged output, and it may lead to a wrong decision, right? You'll be like, okay, so my model right now is really underfitting because everything I give it to it, it almost always produce me a dog. Does that mean that I overtrained my model? No, it just means that your data is unbalanced. So you actually want similar data for validation set and training set. And the last but not least, test sets, essentially after you think, okay, so my model right now is golden. I think it's ready to output something, or I think I actually need to test it in a reality sense of the setting and see whether it actually, give you your desired accuracy or such. Usually we want the accuracy to above like an 80, for example, to say that, okay, this model is actually kind of good, or, is kind of working. To tell it's working, usually you just need like a 65, 70, or just compare it to a, to a comparison set, or just like a baseline model, that's usually how we do it. But the test set means that you actually want to see. So you think by using the training set and validation sets, you already fine-tuned your model. Now you're ready for the outputs. Then at the very last stage, you don't touch anything from the model. So you basically froze it and put it into the test set and see the final testing outputs. And that is where it becomes interesting, right? So for example, you fine-tune your model and you get like 93 accuracy. So you think it's pretty good. And then you start to test it. You want to test it out. And by inputting into your test set, you get like the 65%, which is not too desired. So the first thing I would suspect is that you have something wrong for your training and validation set of that, because that should not happen. Test sets should be divided from the exact same group of data, and therefore it should produce similar outputs according to the validation set. But there's also one other possibility, is that you overtune your model. That means that although, like for the training set, your model keep like updating its weight to it. If you run, for example, 70, 80, 200 epochs means I'll talk about it later. So we're so basically if that means that if your model sees the whole training set for 100 times, 200 times, essentially it overadapt itself to of your given group of training set of data. And that's the same for the validation set of data. Just because sometimes the human look at the validation set of data and they can actually tune their learning rate, their batch sizes according to their needs, and they find essentially the best way to fit this model to your given group of set of data. But actually you don't want to do that. You want a generalized model that can actually adapt to any given situations, right? So in this case, we use the test sets basically to predict whether you overfitted, or use it as a standard testing line to basically simulate the actual reality for this model. So in the process, the test set should only be read once. If you think, okay, shoot, I screwed up, I need to retrain my model, then you can reuse the test set. Because right now, if you reuse your test set, what's the difference between test set and validation set right now, right? You also humanly look at your outputs of your test set, and you'd be like, oh no, my model performed not that well, so I need to go back and adjust the model and make my model adapt to the testing set. That's not right. All of the test set you should only use once. So that means that if you have to go back and come back again for a test set, you essentially need to find new tests, or you just need to sort of do some image regulations on it and turn your original test sets into something new, and then you can use it. Cool. Does anyone still have questions regarding training, validation, testing sets? Because I think this is actually the very fundamental basis of model training. Are you good? Good. Sure. Let's go on. Okay, so I think this is pretty self-explanatory, right? So fitting models, how this model fits. If you have taken linear algebra before, or if you have used MATLAB before, I mean, they probably ask you to do lab like this to see if your predicted regression actually fits the given data points, right? If you actually have, for example, in this case, like a sinusoidal curve like this, and you give a linear outputs, I mean, it kind of fits, but it's underfitting. That means that your predicted results is not exactly following so that basically it means that your predicted output does not fit into a given data pattern. It fits in very roughly and it's not producing a good output. So typically when we're training in this case, what happens is that we'll see a low accuracy just because it's actually not fitted, and a very high loss. High loss means that your predicted output is far from the true label, okay? And for the middle part, so what is the good model means? It means that it kind of fits the data, but sometimes you see like the line is not exactly aligning up with the model, and it's not taking account for some of the outliers, which is very low on the y-axis right there, and this cannot just fit in the data trend. So it's able to drop those outliers and just produce a generalized trend for your data pattern. So that's a good model, because that means that in your training process, you usually get a high accuracy and a low loss. That's what you want, okay? And overfitted, apparently we all know that's not right, because we actually fine-tune our model and make it fit exactly every single data point that's given to us. But as we all know, reality is that there's a lot of noises that's in the given data. And usually when we are using machines or when we're like producing data ourselves, they're not fine-tuned. That means that there are usually noises or outliers or mistake happens when you generate those data or when you collect those data, or those data might not just have a trend, So you don't want your model to overfit it to the given data such that when you're given a new set of data, when new noises are introduced, your model are unable to adapt to it. So this is what it means. So for an overfitted model, when you're training it, I usually have a very, very high accuracy. And usually when you're using a testing set, you will also have a high loss. Cool. Next step. So this slide, I kind of just put it there to kind of want you guys to understand the notion of global minimum and some sort of local minimum. So sometimes when we're finding a solutions, your weight works, but it's not the best way that it can work. So for example, it's producing like 77% accuracy right now, but it can actually be higher. It can actually be much higher just because you can't jump up, you can't escape out of your local minimum and find a new global minimum. That means that the best weights for all of the combination that you can think of, for all of the number that you can think of, it will produce you the best results. So I don't want you to think that you always want to find a global minimum because you never know if your weight is the global minimum, right? So that means that essentially every single time you just want to find a minimum that basically fits your standards. So for example, you just want a 70% accuracy because your model is actually, you just want to use it as a baseline model and see if your data can actually fit to your, if your model's predictive result can actually fit. Then it's, you kind of just, you don't need high accuracy. So you can just find some sort of minimum that can give you basically the thoughts. Sometimes we're training, we don't just design the model and go ahead and just train it. That's not going to work. So basically you need to make sure that your model can overfit when you compare it to a baseline model. So sometimes it's just like a simple MSE algorithm, or sometimes it's just some sort of algorithm that's not random inputs. That means that if you're given like a binary classification test, it doesn't give you exactly 50%. It gives you some sort of like 60, around 60, 65, but it's actually not that good. That's called a baseline model. When you compare your model to the output of that model, that means that you want your model to be better than that model, to say, okay, so now my model is actually trainable. Data train that we pick up is actually working. For example, if we have like a 70 accuracy, and if we can overfit our model to the data, that means that we can actually know our model is picking up the trend. That means that our training is actually working. So sometimes we use baseline, sometimes we first try to overfit our data. I can show you later using the lab. We'll just jump to the next topic. So this one is how to gradient descent. So this is actually how we train the data. The thing showed here is called mini-batch, but actually I don't want to talk about mini-batch first because it's actually the most common way used for the training. And there's a lot of other worse way to do it. And I want you guys to know why it's worse. So here it is. There's no graph because I'm gonna handcraft it. I can't find those pictures online, so I'm just handwritten it. So how to gradient descent. The first step is that we have a large group of training data. I'll call it T. Okay, this is your training data. You have a large group of training data, and the first step is I'm gonna talk about batch. So it's called, sometimes you got like some of the most common ways stochastic gradient descent. Sometimes we use mini batch, and this is batch gradient descent. Essentially, in short, what it means that your model is not going to update itself each time when it sees a data set, but instead it's going to calculate the whole loss. It's going to calculate the loss each time when they see a data set, and they just go to the next one. Calculate the loss. You don't update, you only calculate the loss. And at the end, you're gonna add up the losses and take an average. And then use that whole average, so a global average, you look at every single one of your data sets and you go back and update your weight, okay? So essentially what it means, you have a whole training set and you're gonna, each time when you look at this, you calculate the loss. So I'm gonna say a loss. And they go back here. Actually, it doesn't go back. Sorry. I just said that it's not going to update itself. So it calculates the loss. another point, calculate the loss, and you're gonna have more things like that. You calculate the loss, and then you do average A V G. I'm so sorry, I'm writing with my mouth. It's like bad. Average, and then you update. You use this average to go back. This is batch normalization. Yes. There's essentially no reason, just because this is a really bad way of changing your model. I want to show you guys the worst way to do it first, and then we can go to a better way. But you can say that this step, when you're updating your model, your each update will be more stable, maybe not. If your data all have the same trend, this might be quite stable, just because if your loss are highly inconsistency. For example, like your update direction are the same. So when you add it up and do the averaging, that would probably be more stable, just because you look at the overall. And when you do the update, you take account all the data points. But let's say that sometimes our model produce a positive loss and sometimes it produce a negative loss, which is almost every single case of neural network training. We can't use this just because the positive loss will kind of just conflict with negative loss, because +1 plus -1 equals 0. You don't want those to be canceled out, because if this weight is producing a positive loss, then you should tune it. You should update your weights in the positive directions. And then if it produces in the negative direction, if it produces a negative loss, you need to tune it in the positive direction. So you don't want those to cancel out, because you want to update those weights one by one. So usually we don't use this, because this is essentially really, really bad. And also, I will have to say that if you update by batches, this will be faster. Just because you're updating your weight less, but essentially, if you're just calculating, just passing your value through the network, that's relatively faster than you going back and update each weight, because each step you have to use the computation graph, which is showed last week, basically calculate the gradient descent and say, okay, I want to update the weight by this much. And you have to decide how many to update and kind of just do that. And if you're only doing that once, that means that your whole update process will be faster. But that also means that you need more epoch to go through, because you have to see the data for many, many times, because it's impossible for you to just update your each weight once. It's not going to work. Because usually if you have neural network, it's data points inside. It's not just gonna, it is pretty much just gonna be randomized. It's not gonna be all 0, because you don't want them to just have the same starting point, because you just want to randomize the starting value of each neuron, each weight of the neural network, and kind of update from there. So you don't want to do this. So you don't want to do that. It's faster. You can consider it as more stable if you have similar data trend, but likely that's not going to be the case. And this is not the way that you want to go. So the two most common way right now, one of them is called stochastic gradient descent. So that means that every single time we're looking at one set of data, one single point of data in a training set, we're going to compute the loss and we're going to go back for every single point of the data, okay? And then you don't compute the average anymore, because every single time you calculate the loss, you update it, calculate the loss, update it, calculate the loss, update it. And then you're updating it for a bunch of times, and you're not considering them in groups. You're considering the individual points. But the drawback of that, can anyone guess? Maybe just a general guess. what happens when you just take every single point into account? You tune your neural network according to every single given training point. And sometimes you don't want to do that because it's going to lead you to the wrong direction, just as what we see in the previous. Let me see if I can get back my mouse. Okay. Yeah, get back my mouse. Like this. What happens when you take every single point of data? You kind of overfit it though. So if you want to generalize model by over tuning your data using the SDG, essentially sometime when you update your weights, it's not going to produce a perfectly fitted model like that, but it leads your overall algorithm to the wrong direction just because one of that data point is off. You're tuning your whole model according to that. So if you're going to look at the update path, which I'm going to show you later, you're going to see a much more curvy graph right there, because your update set is essentially not stable. It's not average. It's not generalized. So you're looking at every single data and basically putting their characteristic, putting the generated, you're tuning your overall model according to the general features or characteristics of that one data point. That's not good. So this is what we use usually in the training process right here, which is called mini batch. So a batch is essentially a group of data. Let's comprehend that way. A batch is a group of data. And a mini batch means that we're not calculating the overall training set in groups, in a large group. So we're not updating our weights on the whole training set. But instead, we're going to divide the training set into a small group of data with basically we use constant batch sizes because we don't want the average to go round. If there's remainders, then we can have maybe one extra small batches, but usually we have a constant batch size. And what happened is that I'm right now for the mini batch, I'm gonna divide this whole training set into small batches, and then these are all training set data, by the way. We're gonna compute the loss for each point of those data because we still need to see every point every single training set points. But then we're gonna, after calculating those losses, we're gonna sum it together and take the average. So we're gonna take the average for each group and then use this average to go back and update our neural network. So now we're actually updating our network much more frequently, yet we're not taking every single point into account because we generalize it using the average operation. Yes. Yes. But usually the problem will be much smaller, because sometimes that's still going to be the problem, but it helps you to generalize your data essentially. So sometimes if you have a larger positive loss and a smaller negative loss, that means that you're going to adjust your model according to that right direction. That's why I say batch training sometimes also work. That's a type of training because batch gradient descent. Sometimes it works because general trend is there, but you don't take the special, negative points into account. That if your algorithm is generally pointing that, it's like, for example, if you have a sinusoidal wave and then it follows a linear trend that goes to infinity, your model will probably pick up the going to the infinity part because that's the general direction where your algorithm will go, right? But it probably will miss some sort of like the downtrend on the sinusoidal part because those side of the model will be canceled out if you use batch gradient descent. But the mini batch kind of take account of that problem just because for each batches it's much smaller, and sometimes you can pick up The downside, like if we're using my hand drawn trend, it's probably, so it's a much smaller group of data. It's less generalized. So that's what we hope to do. But it's just decide, give or take, it's a decision made by you. You can, if you have like a data that have a lot of trend to look at, sometimes you might decide, okay, now we maybe need to use stochastic gradient descent, right? If we have so many trends and we don't want an overgeneralized answer, okay? So I hope that makes sense to you guys. And I'm just gonna show you the level diagram for this. So for batch, stochastic, and mini batch, we can see that essentially, let's look at stochastic first. It's we're taking a lot of steps, much more step, and the path is much more curvy, right? Because we're actually taking account into every single data point, so it's not generalized. Our path to the highest points, this is the level diagram. We want to go to the highest points, which is the some sort of minimum. And by using the stochastic trend, we're taking the path from one direction, and we update our model according to each point. But that obviously problem that sometimes data doesn't point to exact trend, which is the global minimum, right? Sometimes it goes to a little bit right, sometimes it goes to a little bit left, but eventually you kind of get there because you update every single time. But sometimes it takes sometimes it's also faster. Sometimes stochastic is faster just because you pick out every single point and you update so many times. It usually give you a faster result, faster training result. But we use mini batch to produce more generalized answer, just because if you compare the green one and the red one, the answer is pretty obvious that it's much more generalized and it's taking much less step. And for batch normalization, I know the graph looks like the batch normalization. The batch gradient descent produced the best results, but in usual, we don't use that way just because it would produce more generalized results. But each time you have to look at every single data point to produce the global minimum. So it's actually not too ideal. But I'm just giving out this diagram to kind of show you the sense of generalization in the step of the gradient descent. And if you look at the stochastic gradient descent, I think it's pretty self-evident that there's a lot of, there's some diverged data point in there. And batch, yes. No worry.
Just so I understand, the length of the vector is dependent on the slope from the previous one. Traveling in that direction depending on that scale value.
Yes. But usually for batch normalization, we'll use a larger learning rate. So usually we are taking a larger step because it's pretty obvious why we have to look at the whole data set to make a step. That means that if we're only making the same, magnitude of a step as the mini batch and stochastic, batch training will be much slower because you have to look a lot more data. So that means that you have to figure this out. Okay. Any more questions? Are we good? Good. Okay. So what happens if the batch size is too small? What happens if it's too large? I think this is actually a really important discussions. Sometimes when we're training, we kind of just disregard the impact of the batch sizes, just because sometimes we decide it at first, and then we go to tune the learning rates and we change the activation functions and add more layers, but we sometimes just don't change the batch sizes because we kind of decided that at first. And if we need to change it, then we'll think of a reason why we need to change it. So knowing why batch size is important is very important. So what happens if the batch size is too small? So that means that we're gonna have a very noisy update each time, just as we see from the last graph, because we're updating our algorithm using a very small increment of the data. That means that our updates essentially is not too stable because we didn't look at the overall trend of the whole set of data. But sometimes we want that because we want to bring noises into our algorithm so it don't overfit. We want to generalize our model. So in that case, sometimes we actually, if you see our model being overfitted to the given data pattern, we maybe will choose a smaller learning batch, such that we increment our algorithm, our model using a much noisy set of data. And then what happens if the batch size is too large? It's too expensive. Because if you have to look at the whole set to make the same set of update, which is the learning rate, right? If you have the same learning rate and you have a larger set of data, that means that you have to look a lot more in order to make that one update. Although it's more stable, but it's too computationally expensive. And sometimes when you're training, it takes hours to train. It takes like, sometimes it takes like 1 night, 2 nights, if you have like millions set of data. And your machine is essentially dies. Like my computer is heavily abused by me, that the performance of it kind of decreased for like 40% right now. Now I can't even play Steam on it because my laptop kind of just died. But it's too computational. Yes. Time and just in general sense, computation resources, like GPU, it's just more expensive. Is sometimes we usually we refer this to time because you can't increment that because it takes time. We are calculating it. You have to look at the data and go back and update. And certain ways to speed it up is essentially get a better GPU, and we all know how expensive that is. And sometimes if you want to make it faster, you might also need to change your structure of loading your data. For example, you might want to pickle your process data array such that when you're taking it in, it's much faster. But keep in mind, we're also using Python. Python is also much slower than C. So all of that it's going to take time. And if you think you design your algorithm very sophisticatedly and you consider a lot when you're designing it, there's essentially no space for you to improve it other than getting a new GPU. But your budget is limited, and the best GPU on the world, I mean, it is there, but we also have a high cap to that. So a hard cap to that. So like there's certain way to improve your training time, but it's still limited. So it's computationally expensive. That's also why when you're actually doing your machine learning course lab, you need to start early because it take time to train. And if your train result never reach your expectation, there's no way for you to fake it. Yes. So because they sometimes ask you to use the fixed random seeds, that means that your data is gonna essentially randomized data is gonna be the same, and they give you the same data. It's reproduce, the same output if you choose the same parameters. But you can't fake that. Yes, you can't fake that. So that means that start early on your lab, and because it's computationally expensive. And the things is that the average log might not change very much as batch size grows, as what we just said, right? What we just said, because you have much more data to look at, and when you're averaging it, it can cancel it out. So your average loss might not change too much, and the general trend, your model will essentially pick up the general trend, but it might lose something because specific characteristic is not being picked up. And the third thing is that the true gradient is not always the best gradient for optimization. And some sort of noises in your gradients can help you actually jump out from the local minimum and find a large minimum. What does that mean is that if we're still on the local and global. Yeah, this is what I wanted. And for this graph, sometimes we're kind of just stuck here, no matter how hard. So for example, if the general trend points to something here, but the global minimum is actually like somewhere around there, we might want some noises in our algorithm, for example, to help us jump to this point. You know, we want something to help you to escape to your capped local minimum, such that noises help you to find a new place to sit down and look at, okay, now where to go. So if you're at this point, now when you look at the graph, you might just want to go, you know, here, which is the global minimum. So sometimes some sort of noises also help you to find a new best set of weights. So it actually, some sort of noises is good for your algorithm because you always want it to be generalized. Yes. And yeah, it also mentioned that sometimes it's converging faster. That's also true if you find a better place to sit at. Yes. You don't want too much noises. If it is like all of the noises and it's pretty predictable where a model is going to do, because it's just pretty much is going to be randomized and like predict something. Because if your overall update trend is not consistent, it might not, you know, just give you, so if your prediction is not consistent, so each time it produces a different loss and doesn't point to the right directions, then your algorithm kind of just stuck in nowhere. And pretty much, if you have an algorithm like that, it's going to give you like around 50 of accuracy. That means that you're just randomly producing things. If we're doing, we're talking about classification tests. If we're doing like a general, like generate new image using the GAN network is another story. Anyway, let's go on. So this is still about the weight updates, and this is something that you can add to your algorithm. You don't have to fully understand the math behind it, but this is just called what we call momentum. So in physics, what we call momentum is that it's something that when you're putting, so for example, you're walking in that direction, you're running, you're accelerating, and now someone push you in that direction, you will still be running, but running a little bit slower. That's what it means. So basically, it accelerates the changes in the same directions, but resist change in the opposite directions. That means that usually, if you have a noisy graph and you want faster convergence, you want faster converging process. And you don't want, you know, in the middle, it's like causing a lot of magnitude. You want that. You might need to add some momentum on there such that it kind of go to where you want much faster, because it's essentially resist changes in the opposite direction of your current direction. So although if you have enough, so for example, if your starting point is wrong, but if you have enough general trend that points you to the right direction, essentially your direction will still change. And now your current direction will align out with the general trend and you go to the right directions. Okay, this is just a way to accelerate the training. It's called momentum. And if you look at the math right here, the W means that it's the weight. So we're saving the mathematics behind the weight, because we all know how we update the weights, right? But the V vector essentially taking account into the momentum, because the V vector, it's updated by a lambda constant. It could be anything that you wanted, and it's timing another gamma constant to the loss functions that's given to us. So we're looking at the loss, the error that we produce, and the derivative of that against the weight. So basically, we're looking at whether our loss, so the rate of changes of the loss with respect to the current weight that we have. So another way to interpret it, just interpret that as the current directions that our data is going. Okay, so basically, each time we're updating the momentum. So if you have enough a trend that's going to that same directions, the V is essentially going to be much de-incremented, and they will produce less impacted results in your like path. And if it is like negative, you have a larger V, and then will produce a larger impact in your path. So if you have like, wait, let me think. If you have a negative loss, if you basically accelerate training, if you have a positive loss, it will basically slow down. It will produce the resistance force in terms of physics. That's how the momentum be. But you don't have to know this math. Yes.
What is the initial value? Like, calculating the previous, like, path, but like, what is it?
Yes. This actually, I'm not too sure, but it's not gonna be zero. Is it gonna be zero? It might be zero. Yeah, actually, I think a randomized value, or actually, I think zero would be a better answer, because we are starting walking. You don't have a momentum because you're standing still. Only when you start walking, I think there's some momentum. So it makes sense to be zero. It could be also, it could be something other than that, but like sometimes we're coding, we put momentum in there, we kind of just put 0.8. That means that basically, essentially, it's the lambda or the gamma constant that we adjust, but not like the initial values. So I think the initial values will likely to be zero. If not, it probably will be randomized. Yeah, I think it will be zero. Yes. Anyway, that's called momentum. We'll see how you use in TensorFlow a short bit later. And here, we've actually already talked about the learning rate before, but I just kind of want to show you what happens when you have a big learning rate, a just right learning rate, and a too small learning rate. So just a quick recap. What is a learning rate? Learning rate is basically the magnitude that you update at each step of your, of your back propagation. That's essentially what it is. It's the magnitude of changes. And sometimes if you have a wrong loss and you have a too big of learning rate, you may be jumping too much, as the first one suggests. You are actually going away from the right directions, because your loss doesn't suggest the right things, and you are actually not taking a single step, like a smaller step. So if your loss are wrong, you take a smaller step, that will make a much less impact on that, because if you're incrementing if your increments by minimum step, essentially it will not make that big of a difference in terms of your training progression. But if you're taking really big learning rates, that means that your algorithm essentially change way more at each step. That means that you might just jump over the global minimum, or you might just jump to some random places. So if you, I don't know if you have heard of simulated annealing before, but that's just a way of, tuning. So it's a simulated annealing. If you're interested, you can search it up. So basically, it also kind of just simulated the physics annealing process. It kind of produced a temperature constant. And when it's really hot, the atoms, the little particles, molecules are just jumping around randomly, and it's not locating itself. And that's exactly what's happening with us at this stage with the big learning rate, because it's taking big jumping, and it's not really looking at the overall trend. So we need to synchronize our overall learning rates according to our needs. And on the right side, just right, that's what we wanted, is taking steady step and going to the global minimum. And can anyone try to predict what happened? Why it's taking a too small step, not a good option? Like, yes. Exactly, it's computationally too expensive. It's not, it's not because we don't want to take a small step. It's just, it will take way too long. And sometimes if you're taking too small too small of a learning, because you're still calculate your derivative, right? No matter what, but it's just a constant that are small. So you're making little changes to your models. So it looks like your model is not getting better, but it might goes to some of the right directions. You just don't know it because you're taking too small increments. So getting the right learning rates is actually very important. And this is actually one of the very easy adjustment that you can make to your hyperparameter. So adjusting the batches learning rate are very easy, but sometimes it will be harder for you to adjust if you have like architecture, and if you change some, for example, you have a convolutional neural network, then sometimes when you changes the layers configurations, you need to make sure the inputs is lining up with the outputs. And finally, when you connect your linear layer to the convolutional neural network, then you need to make sure your number of parameters is actually right. So that means that you actually need to calculate it. That's actually a hard change than the learning rate. So if you're just gonna adjust your hyperparameter, I mean, I would suggest you to start from learning rate and maybe batch sizes. Learning rate usually makes the most difference. Yes. For easy lab, for larger lab, I like if you're actually generating, like if you're using the generative adversarial network, that's gonna be a lot different in this case, because there's also like there's discriminator and there's generator, just a lot more model to train, and it's generally just much more difficult than this. So we're just not going to talk about that. We're going to talk a little bit that in the winter term, and I promise you we'll have a lot of fun with it, because we'll actually do a whole lab on the generative adversarial network where we'll generate, I think it's like generates cat pictures, but we'll have some fun with that. But so far we'll just get our beginning stage right. Yes, are you? Oh, hi. Oh. Okay, so I'm just gonna show you a little bit. I kind of put a GIF on there to show you kind of what it exactly is like learning rate, okay? And the learning rate is when you start at the converging stage, that's what you wanted. You have the right set of learning rate, and you're going to the global minimum, okay? But if you have a too large of learning rate, you know, sometimes you jump at the wrong directions, because when you're updating it, you go to the right of the curve, and it suggests you to go to the left. And then you take a bunch of steps, and you kind of just like back and forth. You're not finding the right global minimum. So that's what we mean sometimes by divergence. And sometimes by using the divergence, it might cause like a very serious issues. For example, if you have even a larger learning rate than this, you might even jump out from this minimum. For example, you land somewhere here. You might land somewhere like here. And then if you calculate the derivative, you will go to the left direction, which is not even a minimum. You know, sometimes at least a problem like that, because your learning rate is too large, so you can't even converge. And sometimes that leads to gradient exploding problem. And you see a lot of that. Probably I think we have one question like that in our today's quiz, but we'll talk about that. So does anyone have problem regarding this step? Are we good for the learning rate? I think it's pretty explanatory. Okay. Okay, so just because the Coursera courses talk a little bit about the Keras SGD, so it's basically doing the stochastic gradient descent. If you have, to be honest, if you have a small training set, using SGD is no problem. And sometimes in my lab, I use those too, because I want to do as much update as I can, so that I don't have to train that much epoch. So sometimes I use SGD. So in this case, we're using, I'm just going to show you, when you're doing training using like TensorFlow, and similarly in PyTorch, you're going to use an optimizer. Optimizer essentially is in what way you're going to do your gradient descent. So in what way you're going to optimize your model, in what way you're going to go back, do the back propagation. So first you said that, okay, I'm just going to use stochastic gradient descent, which means that I'm going to update my algorithm using each data point that's given to me. And I'm having a learning rate of 0.01. So I'm updating the magnitude of my learning rate is 0.01. But sometimes, if you have a lot more points than that, and you want to make a larger, yeah, hi. If you want to, yeah, that's okay. That's okay. I think there's one more in the yeah, Ariel just got dropped in. So for the learning rates, each time we're only updating 0.01, but if you have a much larger training set, or for example, if your like data point is more scattered, sometimes you want to take like maybe 0.001, maybe 0.001, 1 to the 1e -5, something like that. But it all depends on the problem prompt and yeah, if you're not sure about it, find kind of like similar scale of problem and kind of just reference their learning rates. It's not a crime to look at others' product just because, neural network, we're still students, we're still learning. So sometimes, for example, we're given like person re-identification problem. Sometimes what we need to do is not actually just trying out rate by myself, because what I would do if I'm given a whole new problem prompt is that I actually kind of sometimes go online and search out what's the standard baseline. What is a really good standard? What is a good base that I can find? And then I'll start from that point and kind of just optimize my algorithm from there. So finding a good rate is actually important. If you can't find any, it's okay, just test it out. It's fine. So sometimes when you're training, it takes like hours to train, but sometimes it takes like 2 or 3 minutes to train. In that case, I don't think there's a problem for just you trying it out just because it will be faster. Yes. And then it says here that it's going to use zero momentum, which is on the left graph over here. So if you look at the left graph and the right graph, the accuracy, so this is the accuracy graph. So you wanted to essentially converge to 1, but unfortunately I kind of just landed at 0.75. So as you see, if you use the momentum, you have a much smoother graph. You have a much smoother graph, although you might not have, as high as training accuracy. That means that you kind of just because momentum is still like generalizing it, so it's like reducing the noises in your training process. That means that sometimes the noises help you to find a much better global minimum, but using the momentum, it helps you converge faster, but sometimes it just help you skip those noises, if that makes sense. And we're not going to talk about that parameter because I'm not including the advanced optimizer in this case, because I think to identify the difference, yes.
The momentum value in the definition, that's a lambda to give, or is that like a starting value?
It will be the lambda or the gamma. Yeah. This is the magnitude of the momentum. So if you have much larger, it will give you a larger momentum. It's not the starting point. Yes. And we're not going to talk about the later parameter just because I haven't included the advanced optimizer in that case, because there's like 1 or 2 that I don't know. So I don't want to give you the wrong information. And if I'm going to talk about it, I need to make sure that the math is correct. And in order to identify the difference of advanced optimizer, there's actually a lot of math involved, because sometimes it doesn't do the tricks on the update to learning rate, but sometimes it kind of just mimic the momentum using logarithmic functions. But there's I think 1 or 2 that I don't know, so I don't want to go into the area. I don't want to give you the wrong information, so I'm not including that in this class. Unfortunately, it's also not on the quiz. But in the next lecture, before I go to CN, I'll talk about a few really commonly used advanced optimizer. Usually the one that's most commonly used is just stochastic gradient descent, and ADAM. So that's the one of the most commonly used one. And okay. Next one is name equals to SGD. SGD is just saying that the optimizer name is SGD. And the other one is just keyword arguments in Pythons, just indicating that there might be more arguments coming, but we're not indicating what exactly are those. So that's KW, ARG are just keyword arguments. Can ignore that terms. Okay, so I guess another thing that it's mentioned is that one of those keyword arguments could be decay. But what is decay? Decay essentially is when you have a learning rate and you put a decay there, essentially you're dividing your learning rate. So your learning rate 0.1 is your starting learning rate. And then if you add decay, your learning rate is essentially gonna decrease as it goes. Why is that? Why sometimes we want decrease learning rate as we go for the training process? Does anyone want to take a guess? Why you want to change your learning rate at a later stage of your training? Yes. Exactly. So we want a smaller learning rate when we actually get closer to the global minimum, right? So this is actually good to have because the decay, we're actually dividing the learning rate by epoch. So epoch in this case means that essentially when you see all of your learning data once, your training data once, that's one epoch. If you see it twice, it's two epochs. So it's just the time that you see the data. You can interpret it as our model gets more familiar with the training data, our decay goes down. That means that our learning rate goes down, okay? So that also help us to converge for a little bit and fine tune our model. So that's basically it for learning rates. And this is just one thing called learning rate scheduler, because as we just said before, we're doing the decay just kind of by learning rate by epoch. I mean, this certainly works as we see the curve kind of smoothing out. But sometimes we kind of just said, okay, we don't want to wait to update until like 10 or 20 epoch. We want to update our weights and want it to decay. So we only want to fine tune after like 10 epoch, 20 epoch. Then we have to write a scheduler ourselves. But essentially, you don't have to look at this code very deeply. But if you're gonna look at it, I guess the most important part is on the right here. This is the first scheduler, and this is just a second scheduler. Okay. The first, the second. This course only use Keras. Keras doesn't allow us to use a lot of so it's not really customized. It's much more limits than actual like TensorFlow as well as PyTorch. It's kind of just a toolbox for you to use, like a pre-built toolbox that can allow some sort of optimization. So if you're going to learn some sort of machine learning course in university, they're not going to tell you to use Keras. Just because this is Coursera courses, they ask you to write things in Keras, so it's easy to pick up and it's easy to code. Anyway, so the first learning rate decay, what it does is that you have an initial learning rate of 0.1 and your drop is 0.5. It's not mean by your minusing 0.1 by 0.5. You're actually timing it to the power. So you're timing to the power of the drop. So 10, you use the math floor function. Do you guys have any idea what is floor function? So it always run down. So you have like 5.8, you give it 5. That's what it is. So in this case, math floor function. So essentially in this case, if you have the, for example, if you have 1 plus epoch drop, so if you have like, you start from 0. So at your 0 epoch, you're looking at your data first time. That's why they add 1, because if you look at it 1, although your epoch number is 0, you already look at your data at 1. So that's why they increment by 1. So you have like, for example, you have if you have, look at, for example, like 6 epoch, now you have 7, and 7 divided by epoch drop. That means that they want to drop the learning rate by half every 10 epoch, right? So if you have 7 and that divided by 10, that's 0.7. And we have the math 4 function that gives you 0. That means that you're not going to drop any, so you're not going to drop your learning rate until you reach epoch 9, which is the 10th time that you're looking at your data. I don't know if that makes sense to you from the code, right? That makes sense. Okay, sure. And so here you're just going to put that into your learning rate scheduler, and now your learning rate kind of decreases by step. Yes. No, that's just fancier. Just fancier math. Yes, yes, yes. And the scheduler, exactly, we count to 10 and we kind of just return to 101. And when we get, so they use the exponential function. So essentially your learning rates decrease a lot, it decrease exponentially, right? So essentially that's what it means. Every single time after 10 is going to use 0.001 and it's going to decrease exponentially. So eventually you're going to stabilize your algorithm somewhere after some sort of epoch. That means that it's essentially not going to update anything. So that's what it means. Let me just clear my screen. We're almost done. We're almost done. Okay. Woo. What time is it? Okay, 2.5. We're doing good. Okay, perfect. So this is just a comparison chart that I can graph on the PowerPoint in the Coursera courses. It kind of show you what happened with the baseline, which is a fixed learning rate without decay. And this is batch size. All of the other happy parameter are the same. We're only adjusting learning rates as decay constant. Essentially, we're only saying that first we're using a fixed learning rate. And if you look at the graph, we have like big drop and jumping around part, right? And if you have momentum decrease and decay, we kind of just convert faster, and also it's more stabilized, because when we're getting to the end there, we're actually having much more small increments compared to the very beginning. And if we use the custom learning rate schedule, which is step drop, we can see big jumpage, big step jumping from 1 to 20. But as we go to the end, as we see, it's actually stabilizing more than, the one with momentum and decay. Okay, because each time it's squaring, That means that your learning rate is actually getting smaller than just, simply dividing by your epoch constant. Okay. And we're getting to the regularization part. But before that, let me just make clear of the batch epoch iteration parts clear again, just so I hope you guys are not confused. Okay, so each epoch, we usually sometimes like when I'm training the labs, I kind of ask my friend, like, how many epoch did you run to get this? Because sometimes he doesn't tell me what's his like validation data. I was like, well, there's no use if you only tell me the training data, right? You're training a statistic, right? Because you could have like 99% training statistics, but your algorithm is still overfitting. That's not good. So I was like, how many epoch did you run to get that? Or if he says no, but I'm testing my validation, my validation statistic is like 93%. I was like, how do you do that? How many epoch did you run? I was like, because for a lab, sometimes I sometimes had a time crunch. I admit, I also procrastinate. So sometimes I don't have enough time to do it. So I only train it for like at most like 25, 30 epoch, and that's kind of the end. And because I need to test like multiple hyperparameter, I need to train for multiple times. So each lab take like hours to do. So I don't have time to train, but some of my friends are really dedicated to get a really good, training rate, because they don't care about the mark, but they care about what accuracy they have. So I can just be like, oh, shoot, dude, how many epoch did it run again? So that's how many times your model has seen the data. And that's kind of, if you run more epoch, is naturally your training is gonna take more times, okay? And iteration is just means that, okay, it's closely related to the term batch. So batch sizes, as we just discussed, is how many group of data are we use to kind of just implement our weights, right? We're kind of dividing the whole training group into small batches and then use those batch of data to update our weight. So that's the batch means. So if you have batches of 20, and if you have, for example, like 100 training data, then you have 5 batches. That also means that you're gonna iterate 5 times to go through all of your training data. So your batch sizes is 20, and your iteration time is 5. So that's epoch, iteration, and yes.
So in one epoch, you go through all of that.
Yes, because your essentially your batches contains your training data, right? But you, in one epoch, you must let your model see every single one of your data points. That's the point of training data set, because you want your model to kind of just look at the same data set and update. Because the reason that we don't use different data set to update every single time, because we want to repeat this process. Usually at epoch 1, your model is basically garbage because it haven't updated to the degree that it can pick up some trend. So if you look at the training curve right here, at epoch 1, at 20, it reached a 70% training rate. But at like 5, it's you see, like, or at 1, your average, your accuracy essentially at like 55%-ish, right? 55, 65, 60, below 60, that's actually not really good. It only progressed, your model only progressed after your model has seen the same set of training set for a long time. And as you see more, your model kind of adapt to it, but you kind of want to break it off until you over adapted to it. So that's kind of like the process there. Okay. And the last step is regularization, dropout. So what happens if you find your model adapt to your data pattern of my words? So you're getting a lot of overfitting signs, but what do you do? The first step is you use dropout. So dropout is very commonly used, at least for deep neural network. Okay, so what I usually do is that when you it not only produce the regularization, so the generalization effect, it also reduce your training time. As you notice, it's actually dropping some of the parameters. So if you drop 0.5% of the parameter, you only have half the parameter left. So that means that you reduce your connection by half. So that's actually really good. You reduce your time, but you don't want to cut it off too much. You're forcing, so by using the dropout, you're forcing your algorithm to pick up the most important one, because you have to have like redundant representation of the same characteristics, such that when you drop it off, you don't drop the important part. Okay, your algorithm, it must be still learning. And I'm just gonna mention that each layer, when you add the dropout, it's gonna be the same dropout for each. Or is it gonna say? Sorry, it's not gonna be the same. So just forget the last sentence that I just said. So anyway, so essentially adding the dropout, forcing your algorithm to learn more about the more important of the algorithm, also cutting down the time. Furthermore, it also helps your algorithm to generalize, just because sometimes we have more connections. That means that your algorithm is learning more characteristic of your current data pattern, right? But if you're dropping off some of them, that means that you're cutting off the unnecessary characteristic, such that your model is becoming a good fit again. Okay, sure, that's dropout. The next one is batch normalization. For this one, there's some problems. Yes.
Basically find like the derivative of the by a certain way. If we're dropping out some of the
Connections.
Does that change how the gradient function will be like calculated, or is it still the same function?
It's just not gonna calculate the disconnected edges. Yeah, it's just not gonna, so if you're, it's essentially, it's not taking out neurons, it's taking out the weight. So it's not looking at those weight anymore. You kind of just, I think, I don't know how Keras are implementing this, but my guess is that they're just gonna like pick a subset of the weights and just not kind of just throw them away, or when we at that stage, we don't look at them. So they probably use a random constant and kind of just use, if this random constant, like they have a 40% probability to become like true, like 60 become false. When it's true, we drop it out. When it falls, we don't. So that's kind of just the probability. Or more likely they'll use the probability approach. They're probably just gonna, you know, take a subset of it and just kind of throw it away. And batch normalization, this is often very, this is also just a generalization. So if your model is overfitting to some sort of data pattern, usually you want to normalize the distribution of data's pattern within that same layer, and with that same within that batch of the data pattern. So basically you generalize the data distribution to make it more generalized, to regularize it. And I'm not going to talk about the probability stuff behind it, just because it gets complicated. And I think it's enough for people to know that this helps to generalize the same batches. And sometimes it also helps with gradient exploding problems. So for example, if you have like, that often happens if you do like natural language processing problem. So you have like gradient exploding just because it's recurring. It's RNN, right? It's recurring, patterns recurring. So sometimes your gradient kind of just disappear, or sometimes it explode. But using the batch normalization, you're kind of just reorganizing the pattern within the same layer each time you're getting to the middle layer part, and you're fixing the distribution such that your gradient descent kind of just stabilize a little bit more. So it sometimes doesn't really reduce, doesn't just let the gradient descent, what do you call those, gradient exploding problem go away, but it kind of decreased the magnitude of that. And it buy you a little more time for the batch normalization. Okay, the next step is early stopping. Then this is probably the last thing that we talked about in this course. In this section. Because sometimes when you train it for a long time, and for example, you already reached like 98%, but then your model starts to overfit, and then your validation accuracy and validation loss start to go up, and your validation accuracy start to go down. That's when you need to say, okay, now my model is overfitting, I need to stop. That means that if you're training for 50 epoch, you're just going to take essentially your weights from epoch 30 or 35, where you feel like, okay, this is the best point that I can have. You kind of just stop there and take the weight from that, but don't go longer. So that's your starting point, stopping point. And then there's another thing called early stopping with patience. So that means that you're going to wait a little bit more, because sometimes it kind of bounce back for a little bit and they go down, we find a better minimum, but it's not overfitting because the validation error and the training error is aligning up. That means that you want to wait for a bit. You don't want to like stop immediately after you identify the overfitting. Sorry, the overfitting trend, but you want to give it a patient period, for example, like 20 epoch. Wait for 20 epoch, I'll be like, okay, now it's now I think I find a point and then stop there. And I think that will be the last thing that we'll talk about. I think early stopping is pretty much self-explanatory. So we'll just go to the next thing, which is we're going to talk about this week's quiz. There's only 3 questions. I think it's actually quite easy. The first question is, which of the following statement is not a reason for adding a dropout layer? So adding a dropout layer, as we just said, The first one, obviously, I mean, is the reason why we added. And does anyone want to take a guess first? But it's okay, just it's okay to be wrong. But yes. Is the second one? Yes, but it's also forcing it to have redundant representation. It does removes the redundant representation because it wanted to have redundant representation because it wanted to pick up the most important characteristic of the algorithm, right? So I think I might be confusing your guys when I said that it removes it does remove the representation, and that's because it has the redundant representation, right? And by adding the dropout, it's because originally, for example, you have 100 characteristics, but now you only have 40 ways to go. So which 40 do you choose? You choose the most important one to lead you to the less loss, right? So you're forcing your way to picking up the most important characteristic of your data and only represent those from the 40. That means that when you cut it off, you might have redundant characteristic representation in your connection, your full connected layer, right? But when you're cutting out the dropouts, you're essentially cutting out the redundant, only leaving the most important part of the algorithm. That's kind of what I mean by the dropout. I think I might be confusing you guys. Sorry about that. And but that's okay. And I will tell you guys the third option is also one reason for adding a dropout layer, just because adding a dropout layer trains an ensemble of models. Sometimes you have like multiple models and you kind of put them together. Then that's when you add dropout, just because kind of different model pick up different characteristics. And you don't want to take all of those. You don't want to take all of those. So you still want to take the most important part of that algorithm and kind of pass it to the others. So that's why we also add dropout layer. It's kind of just forcing, if you have originally like a larger selection group, it's almost like a tournament, right? Oh, you have like the regionals and you go to provincials. You have a larger group of candidates at the initial stage. And when you add the dropout, only the better one goes to the next stage. That's kind of what I mean by the dropout, because it's just deselecting the bad ones. But it's not sometimes. So that's why I kind of say it's the network to have redundant representation, just because when you're selecting the dropouts, it's selecting randomly. So it's not like each time at each epoch you drop out the same weight. It's like each epoch is like different weights drop out. So you don't know which one you're gonna drop out. So you're gonna have you're gonna reproduce the connection that represent the most important characters of your data. And then when you drop out some random one, there's a larger chance for you, if you have redundant representation, that you'll keep the most important characteristics of your network. And that's what it means by that it forced the network to have a redundant representation. And the last one is adding a dropout layer make the network more expressive during training time. And that is the one that is actually wrong. Because it doesn't make the network more expressive during the training time. In fact, it actually kind of because expressive, expressive means, it means that it's giving you an indication where the network is going. But as what I just said, that this is a regularization algorithm. So dropout, you're dropping off some of the weight from your network. Sometimes you even drop out the important ones. It gives noises. It does give noises to your algorithm. That means that when you add dropout, you're going to see the reflection much larger. So in that case, it does not make your network more expressive, just because you're going to see much more noises and much more reflection in the if you add dropout in your model. So it doesn't make your model more expressive, but instead make it more generalized. I will say that. So it's not. So when you're seeing your model going around, it doesn't mean that when you look at, you know where it is going, right? It just means that it kind of you hope it's stabilized at the later stage. But right now, if you look at it, it's gonna be more noisy, so it's making it less expressive. And the next one is, it's a TensorFlow question. So it's essentially that they build a model. So let's actually read the model for a little bit, but it's not too important in this case. It's just a fully connected layers, just MLP, multiple layers perceptrons. So first, it starts TensorFlow Keras sequential. Sequential means that it's in sequence. It's giving a sequence of neural network layers. And the first thing is that you're gonna have a dense layer. Dense layer means what I just said. It's a fully connected layer. It's like a number of perceptrons in it. And it's using ReLU as its activation function, and it has 784 inputs, and it's out. It has 784 linear inputs, and its output is 512. And the next one we added, then you don't know the input shape because you already know the input shape because the last dense layer is 512, and the next one is going to be 556, and the next one, the input for the third layer, the input parameter input shape is going to be 256, and the output is going to be 128, because you only have 128 neurons, so you're connecting 256 to 128 neurons. And the last one, you're using a softmax to find, essentially, you're concatenating them together and find the softmax. So after that, you name this sequential 10. So this model just named sequential 10, and you have that much total parameter, and you have that much trainable parameters. So all of those parameters are trainable, essentially, because you didn't add dropout. Okay. And that's essentially what it means on the left side. I will actually, after this, I will also upload this PowerPoint to the Discord channel. If I think for you guys, just because I think in person, I didn't have the Zoom chat to distribute it. So I'll also upload this to Discord channel. And later, I think Mandy will upload this recording as well as this slides to the website. So you have all of this material accessible to you. If you have any further questions, you can just email me or Mandy and we'll answer your questions. And the training log on the right there, it kind of just disregard the any epoch before 20 is because it's gonna produce garbage. I haven't reached the convergence stage. It's still kind of just climbing up to the best points. So at epoch 21, it's producing about 91 accuracy and 91 training accuracy and 86 validation accuracy. And at about 30, you can see a sudden jump because you see the training accuracy become about 96%, which is normal. It fluctuates around, right? It's normal to see a decrease for a little bit. But it's not normal to see the validation accuracy become 0.103. That means that you only have a 10% validation accuracy. That's bad things because the last stage, you still have an 88 validation accuracy. Well, next thing is that you see a 10% validation accuracy. That means that something has gone really, really wrong in the weight update process. And the question I was asking you, what is a possible recommendation that can improve the results? So like all that apply. The first thing that come to your mind is that you can apply early stopping, right? Because it just changes at one epoch. So there's a clear indication for you to say that, okay, I can maybe just stop there and let's call that an end. And the next thing is that, so would add regularization terms such as dropout, batch normalization, bridge and lasso, etc. would help. It would actually help maybe a little bit. Why is that? So if you see a higher training accuracy and a much lower validation accuracy, what does that mean? That means that you are overfitting. you're overfitting your data. And because your validation data set just kind of just go down because your model never see those data. So it overfits your training data, but unfortunately, your validation data is indicating that your algorithm is wrong. In this case, we can add regularization algorithm or add regularization terms to kind of just prolong this process. We basically generalize data pattern and make the algorithm can adapt to the pattern slower. Okay, it would work, but it will not change the fact that that like it suddenly goes down at one epoch. That's really rare to see. Usually you see a trend, but it's just go down. And that's actually a clear indication of what's wrong in this case. I think it's quite obvious, but first let's just look at this question because that's what the next question is going to be. Yes. Region lasso is other ways of regularization process. So basically rich is kind of like sometimes is rich, if you have done the assignment before, is kind of like a step function, kind of like that. So, and lasso, I'm not too sure. It's just a type of regularization terms. And in this case, I might know the other terms of lasso, but I don't know what it's indicating in this case. Usually there's other more commonly known decay, like regularization term, like L1 and L2 like weight decay, things like that. But it's more mathematics, so I didn't include it in this because this is a 2-hour session. I think everyone is tired when they're sitting there. So I just think more intuitive, and this is enough for you to pass the Coursera courses. I think I kind of just modify it to a degree that this is fit for the study group's purpose. But if you guys are curious about more mathematic terms, you can just email me and I'll try my best to give you an answer. And I'll give you some extra reading if you're interested in the weight decay stage. And if you're more interested in the mathematic aspect, I can also give you some recommended reading. And training more epoch will not help in this case because it kind of just stuck in the overfitted stage. And the increased learning rate will not help because yes. Increasing learning rate will not help just because actually in this case, the next question is like, it's the same problem prompt. The next question is, what is the most important fix to recommend to your friend? In this case, for me, the first thing I would say that I think this is actually something wrong with the learning rate. Because if you overfit it, if this is a regularization problem, you will essentially still see a trend, but it goes wrong at one epoch. That means you must have updates your whole weight to something else that can produce such a drastic changes. You know, this is a huge changes. If you have like a suitable learning rate, it's impossible for your algorithm to go wrong in like only one epoch. In one epoch, that's a huge changes. And that's why I said that I think this is a learning rate problem, just because if you see this huge drop at the 30th epoch, that means that it's most likely among all of these among all of these options is the second last option, because it's gonna be something wrong with the learning rate, because you have such a big learning rate that when you have the weight updates and you kind of just update your whole weight into something else because you have jumped out the current local minimum and you go to somewhere that you don't know where it is. Okay, so that's essentially what it means. And the larger architecture will not help in this case, because larger architecture means that you're going to add more layers. And usually what happens, why you add more layers, that you want your model to be deeper. And sometimes you might have more connecting parameters. Sometimes you might have more connections. That means that you want your algorithm to be more adapted to your training data. So in this case, this is kind of like a variation of the over-adapting pattern. It's an overfitting pattern. So in this case, I will only suggest the first one and second one because all of the other options are wrong. Do you have any questions regarding the this problem? Good, good. Okay, so the last question become quite self-explanatory as well, right? Because the last one is what is the most important fix you recommend to your friend? As what I just said. I mean, early stopping would fix it, but you're not sure. If you take a smaller learning rate, you actually may converge to something that's much higher. You may have a higher accuracy. You may produce a much better model that you can find, right? So that's not called a fix. It's kind of like if you use early stopping, it's kind of you're not fixing your issue. You're still having your issue, but you kind of just okay. I just want something that's workable. I don't want to fix it. Let's just take this and let's try to find the best that I can do in the current bad situation. So the most recommendable fix for me and for you guys, take a guess what it is. Yes, it's the first option. And that's the end for this section. And the next one, I'm going to show you the full code. Actually, I still have 5 minutes, so I don't think I have time. So the first thing I'm going to do next class is that I'm going to show you a full training loop that's related to the whole training process. It's going to be pretty cool. It's going to be about 100 lines of code. I will not go through all of them, but I will let you guys identify the key step of the training loop. And feel free to just grab my training loop to train your things because it's pretty standardized process. It's also on my GitHub. If you're interested to check it out before it, you can also go to my GitHub and just get my codes. Yeah. And next session, we're going to talk about image, CNN. It's going to be pretty cool. That's convolutional neural network. You're going to learn how exactly are we doing this thing that applies to image because, you know, image are pretty differently structured than the standard, you know, linear data that's given to us. So we're going to learn a lot about those, how we're going to treat image and how we're going to update weights that specifically apply to one image. It's quite different than how we're doing the linear connected layer because right now we're still at the stage that we're only looking at fully connected layer, aka MLP, multiple layer perceptron. But in the next class, we're going to use kernels and we're going to take stride to see different part of the image, and it's going to be pretty cool. And next class, I'm also going to show you full code example on MLP. Likely, it's just going to be embedded into a training loop as a addition to it. And then we're going to talk about what is kernels, what is paddings, what is stride. And if we have time, I'll attach full links to it. And I'll explain what exactly is those in the next class. But hopefully after the next sessions, you can actually build a small like image by binary classification algorithm by using my code example. And hopefully we'll get there. If not, we'll add more extra sessions and we'll analyze maybe a Kaggle project together. So let's do that. So if you have any questions, I look at the assignment for week 2. Mindy, are you still there? You can stop the recording.
Okay.
Okay, thanks so much. And for next